One of the things that we always want to be cognizant of when we're looking at polynomial functions, okay? And then I guess we should mention what polynomial functions are. Polynomial functions are any function that includes multiple values of x that doesn't include any rational values of x. So we're not going to see any x's in the denominator of a fraction. Okay, we're not going to see that. All we're going to see is one single line. You can have fractions, right? You can have 1/2. You could even have x over 4. Like, that's okay. What you can't have is x in the denominator. So a polynomial function, okay, first and foremost, the domain of a polynomial function is always infinite, right? It's always from negative infinity to positive infinity. You're not going to see any breaks in this graph. You're not going to see any asymptotes. You're not going to see any holes because we can plug in x here and here. We're not going to see any radicals. Okay, that's another point. We're not going to see anything, any x values under a radical, okay? Because then we start to break the domain, right? One of the primary characteristics of polynomial functions is that their degree is infinite, all right? What we want to look at when we're looking at polynomial functions, and something that makes us a little more well-rounded with this, is we want to look at the degree and we want to look at the leading coefficient, okay? And when we talk about the degree of a function, so let's start with odd degree. The odd degree polynomial functions have their highest exponent as an odd number. And this 2n plus 1, this is the for values of n that are greater than or equal to 0. This is how odd numbers are typically expressed, okay, in college textbooks, in calculus textbooks. And then we use values of n for 0 or greater. Like if n is 0, then this whole value is 1. If n is 1, 2 times 1 is 2 plus 1 is 3, right? So now it's a third power. Now, what happens after that? Not necessarily a concern. We're only talking about the highest exponent. We typically write the highest exponent first, but you will get into some situations where they're trying to screw you up. Well, they'll do something like this, okay, right? The degree of this polynomial function would be 4, right? Because even though it's not first, it's still the highest, all right? Now, don't confuse odd degree functions with odd functions, okay? We've talked about odd functions before as passing through the origin, right? And having that rotational symmetry about the origin. That's an odd function. Odd degree functions don't necessarily pass through the origin. They're going to share this similar shape, but they don't pass through the origin, okay? A couple of characteristics about odd degree functions. If what we call the leading coefficient is greater than 0, meaning positive, okay? If we have a positive leading coefficient in an odd degree function, the behavior that you're going to see is it falling to the left and rising to the right. And notice how I've drawn this. Anything can happen in here, right? There could be all kinds of bumps and maximums and maxima and minima and whatnot in here. But the end behavior is falling to the left and rising to the right. And the way that we describe that is kind of calculusly. As x approaches negative infinity, so as we move towards the left, as we're the left end behavior of this graph, y approaches negative infinity. That's what it means to fall to the left, okay? And as x approaches positive infinity, meaning moving to the right, the y values are increasing as well, okay, going towards positive infinity. This is what we refer to as end behavior, okay? So for an odd degree function, the end behavior would be thus: if the leading coefficient is greater than 0. You'll want to write this down, okay? The leading coefficient is the coefficient. I'm not going to write it out. I don't have a ton of room here. But the leading coefficient is the coefficient of the term with the highest exponent, okay? So you're going to hear something referred to as the leading coefficient test. The leading coefficient test is just look at this number and determine the end behavior based off of that. All right. So if we can switch this up. So what do we do if that a value is less than 0? What do you think? When we have a negative number in front of our highest degree term, what do you think we're going to do based on what we've talked about with transformations, right? We're going to take this graph and we're going to flip it over. Okay, so like so. If we flip this graph over, now the end behavior changes with that negative leading coefficient. So now, as x approaches infinity, the y values, or excuse me, as x, let's say negative infinity, as x approaches negative infinity towards the left, as we move to the left and left and left and left, this graph is moving up. So the y values are approaching positive infinity. As x values are approaching positive infinity, meaning towards the right, this graph is going down. The y values are approaching negative infinity. So we would say, I'll write this down here. I didn't write it up here, but I'll write it here. We would say this is left end behavior. Okay. And the left end behavior, we would say, rises to the left and it falls to the right. Okay. So this is our end behavior that you'll see once you're involved in some of the assignments here. All right. We'll talk about even degree functions and their end behavior here in a second.